Hi everyone. Today's topic is subtype polymorphism. As we discussed before, polymorphism is for various shapes, various thingies. And now that we are talking about types, we learned parametric polymorphism already, where when we have for all alpha dot tau, there's only one shape, but this shape represents many kinds of types. So when we have some type tau, there may appear alpha, which is a type parameter, not like a function parameter, but type parameter. This alpha is bound here. And when we have alpha in this tau, when we change that, replace that, instantiate that with some other type, we can have various types, meaning that for alpha dot alpha arrow num, this represents many types, like replace alpha with num, then it's going to be num arrow num. Replace alpha with bool, then it's going to be bool arrow num, like that. There could be many types by instantiating alpha in this parametric polymorphism. And today we are going to talk about subtype polymorphism. As in Scala or Java, there is a type hierarchy, and the top type could be object in Java or any in Scala, and that's going to cover various types like num type or collection type, or some other things like that. And num may have int, float, real, and more. Collection could have list, map, set, and more like that. These are subtype polymorphism that we are going to learn today. So let's think about some cases where we want to have multiple values for some concept. For example, a student may have student ID and the age. Then we can ask, like, what's the ID, student ID of a given student? Then we may have multiple students, right? So say the first student ID and age. The second students have a different ID and age, and we may want to have some operation on their ages. What if there are many students? We may not want to have these kind of copy and paste style. I already told you it's a really bad style. Instead of that, we'd better have a specific type for that collection, right? Let's say it's record. Record or class, struct, whatever you call it in your preferred language. In today's lecture, we are going to talk about record. Then, let's say student is a record which has two fields. Student ID, which is a number, and age, which is again a number. Then we can construct a record value, right? We can have multiple record values for that. This is going to be the language for today. Again, FAE with records with types. FAE with if-zero expression and record with types. So these red things are about records, right? So two language features for records and one type for records. The first one is about creating records. The second one is about using the record. How can you make a record? By having this curly braces with some fields information. A record is a set of fields. Each field has a label, name, with its value. So when we have open L1 equals E1, L2 equals E2, Ln equals En, we are going to evaluate E1, E2, En and get their values V1, V2, Vn. That's gonna be a record with n fields. When we want to use a record value, we can have this access syntax E.L, meaning E's value should be a record value, and that record would better have a label named L. Then E.L gets the value of the label named L in this record value of E. And the type is this. Again, it's a set of fields, so it's curly-braced. It's a collection of n fields, L1 to Ln. Each may have tau 1 to tau n, meaning that each field may have different type. They do not need to have the same type. So what's the semantics again? I already told you, but let's describe that in a formal way. Under a given environment, when we have this record construction expression from L1 to Ln, whose values are the values of E1 to En respectively, then how do we get the value of this expression? As I said before, we are going to evaluate each sub-expression. E1's value, let's call the value V1, The last expression, En, let's call the value of that to Vn. Then we are ready to create a value, record value, consisting of n labels, n fields, and the first field labeled L1 has the value V1, and the last field Ln has the value Vn. So this is a record value, right? Now you know how to extend the syntax of value for T-rec-FAE. T-rec-FAE. You do that by yourself. Do it yourself. How do we interpret an expression whose value is record value and get the value of the field labeled L? Okay, that's the semantics. Then you know the value of E should be a record, and in that record, exactly one field should be named L, and then we can get the value of that. Nothing so surprising, right? So let's see. You should be able to draw this kind of derivation tree for a given set of rules. When we have this expression E dot label, what's the value? Oh, E dot label. Then we need to evaluate what? We need to evaluate E, whose value should be record value. So we need to evaluate this record expression. How do we evaluate this record expression? We need to evaluate each sub-expression. We are going to evaluate those expressions because they are just numbers. We get the number values. We construct record value. Even though this left and right look just the same, on the left is an expression, on the right is a value. Now that we have this value, we can check whether it has this label H. Oh, that's good. Luckily, we have that. Get the value. That's going to be the value of this expression. Okay. How about type checking? Right? How about type checking? So, let's see one more time. We have this record expression because we know how to interpret this expression based on your experiences from project number 1 to project number 3 that was out on Monday, right? That I emphasized multiple times that you do better start earlier than later, right? When you know on operation semantics, it's highly likely that you should be able to write down typing rules. Why? Oh, remember, note that under some environment, when we evaluate an expression, then it has some value. And depending on this language construct, we may have some rules like record expression and field access. Then we can write down corresponding type environment with that expression has type tau, and we can have similar thing. Because of this similarity, this type environment gamma is an abstraction of this runtime environment sigma, because this runtime environment sigma maps names to their values, and type environment gamma maps names to their type, right? So we have this relation. So how we evaluate this part has correspondence between how we type check it. So back to this typing rule, because how did we interpret this expression? We interpreted each sub-expression, get their values, and then construct a record value. How would we type check this one? Yeah, you can guess, right? For each sub-expression, we type check them from E1 to En, get their types from tau1 to tau-n, and construct a record type. That's it. That's simple, right? This record type is a collection set of fields labeled from L1 to Ln, whose types are tau1 to tau-n, respectively. How do we type check record field access? As with this operation semantics, we type check this expression E first, and that should have type record type, not num type, not arrow type, but record type. So it should be record type. In addition to be a record type, that record type should have a field of name L, the same name, so that we can get its type. Right? So far so good. Very simple, as expected. So again, we should be able to draw this type derivation under a given empty type environment. What can we do? What should we do? We should type check this field access, record field access again. Then we need to type check this record expression again. In order to type check this record expression, we need to type check each field expression. Luckily, their types are simple, num and num. Out of that, we construct record type. In the operation semantics, they had values like this, but now it's type checking. We are abstract that to num. So the record type is like that. Again, when we have this record type, we need to check whether it has the field named age. Oh, good. We are going to get the type. That's going to be the type of this field access. So far, so good. Yay. Then what can we do with this? We can run it and type check it using records. This is a function application. The argument is a record expression with only one field whose label is B. Okay, and this is a function which expects a parameter of type record, which has one field of name A. So in the body, we know that X is a record which has one field of name A, so we can access it. So far, so good. But even though this function expects a record with the field named A, we pass a record with one field named B. It's gonna be a problem, right? You see the problem. So does the expression cause a runtime error? Yeah. Is the expression well typed? No, that's good. It's a bad program. Bad. Why? Because it causes a runtime error, and it's good that we reject that. Our type system rejects this code because of this difference. So far, so good? Yeah? Do you see why it's not well typed? If you don't see it, you should be able to check it. Okay? Let me emphasize one more time. This is a function call, right? You know how to type check E1, E2. right? You should be able to say that. Right? And then what? We said that, oops, this function part should be an arrow type, tau1, arrow tau2. This argument part should have some type, tau prime, and tau prime and tau1 should be the same, but they have different type. That's why it is not well typed. I gave you a hint. You'd better be able to write down this type derivation why this is not well typed. Okay? Yeah, that's the minimum before the final exam. Then what about this? So let's look at this code. What is it? It's again a function application. Okay, the first part, it's a function expression which expects a record which has a field named A, and the body is gonna access the field named A. The argument expression is a record which has two fields, not one but two fields, and those two fields are named A and B. Does the expression cause a runtime error? Oh, let's see. X's value is this record expression. Let's forget about the type annotation because it's a runtime thing that we are asking, right? X's value is this record value. And then in the body, hey, you record X, give me the value of A. Oh, that's 1. Wow. It does not cause a runtime error because the parameter X expects a record which has just a field labeled A. It doesn't say anything about the other fields, like no more fields, like that. It didn't say that. It just said that I want a record with a field named A because I'm going to use the value of it. So when we pass a record with a field of named A but extra, it does not throw an error. Do you see that? Yeah? Yeah. The more the better. But is it well typed? No. Why not? As I told you before, what's the type of this expression? It's a record type A num B num. This is the type of this argument expression. What's the type of this function expression? From this record type to num, right? So the parameter type is that, argument type is this. They are not the same, so it's a type error, even though it does not throw a runtime error. Then what's the current situation? This is a perfectly good program, but our type system is limited. So our type system is not powerful enough to accept this reasonable code. Then what can we do? Extend the type system as usual. That's with subtype polymorphism. We want to use this record expression or record value as a value of this time and this time and this time at the same time. So this expression has two types at least. A record with one field or a record with two fields, right? We need a new notion of polymorphism, meaning a type that represents both of them. Subtyping. That's the topic for today. Subtyping. Subtype. If any value of type tau can replace any occurrence of a value of type tau prime. One more time. If any value of type tau can replace any occurrence of a value of type tau prime. If any value of type num, type int can replace any occurrence of a value of num, then tau is a subtype of tau prime. Now, int is a subtype of num because int can replace any occurrence of a value of type num. So when we have num and int and say real, There are operations that we can do with numbers, like addition and subtraction, like that. There are operations that we can perform on integers, but not on real numbers. Yeah, there are operations that we can perform on real numbers, but not on integers. So they are more specific types, but they are both numbers. So some simple operations that can be performed on both integers and real numbers, we can put them on number instead of int and real. That's what? Supertype. So tau prime is a supertype of tau. Tau is a subtype of tau prime because int and real, they are numbers. They can replace any occurrence of a value of type number. So we write such a relation this way. Tau is a subtype of tau prime. So when an expression has type tau into a real, okay, more specific type, and there are less specific supertype, then we can say that that expression has that supertype. When we have 42, right? And we know that 42 is an integer type, but we also know that integer is a number type. Then 42 has number type, meaning that 42 has two types, int and num, and maybe more types. That's subtype. Subtype rules have several features, properties, I guess, which is reflexive, meaning a type is a subtype of itself, because a value of this type can replace any occurrence of the value of itself, right? And subtype relation is transitive, because when one type is a supertype of the other and the type is subtype of another, then the most specific one is a subtype of the least specific one. That's what we mean by transitive. If you do not know what reflexive and transitive mean, you'd better go back to the discrete math. Subtyping rules. Now that we have subtyping rules, we'd like to extend one more thing. Record expressions. Between record types, they may have some subtype relation. What's that? In the previous relation, this record with labeled 1 to n and this record with labeled 1 to n, they are just the same. But what we want to do is that when there's extra field, if all n record fields are just the same, they have the same time, then even when we have extra fields, that is a subtype of less specific one. More concretely, when we have these records with two fields, right? We know how to type check this. We already done that before. Then this record with two fields is a subtype of a record with one field named A. Do you see that? The same thing is a subtype of B:num, right? And the same thing is not a subtype of C:num because it does not have C. Because of this subtyping relation, we can say that this is the type of record with only one field. That's why we can allow the previous example. And similarly, we can have more, like this is a functional application, right, with record expression, this time a record with three fields. And this function expects a parameter of a type record with three fields. That's good. And then in the function body, there's one more function called x is that thingy, and the function inside expects a record with only one field. Does the expression cause a runtime error? wait, x is that, and we want to get the value of a. Oh yeah, that's going to be 1. No runtime error. Is the expression well typed? Yes, because of that added subtyping rule. And how do you know? You'd better write down that typing derivation of this expression. Do it yourself. Very good. So far so good. Let's take a break and continue with the second part of subtype polymorphism.